So let's move into our last section now. Again, as I said before, this should take about 35 minutes to get through. We're about 80 minutes in, so that should push us to about an hour 50, which is about perfect. So let's push through this last little bit and go through our bonding. Now, bonding is super duper important. I cannot stress it enough how important bonding is. Bonding is like the description of everything. Bonding is just super duper important. Like, I cannot describe to you how important bonding is. Like, it's really, really important to know your bonding. So please know your bonding really well. It's going to come up. It's something that comes up in your main HSC chemistry all the time. It comes up in VC chemistry, which I tutor all the time. It is just, you need to know it. So you have two sort of main types of bonds. So we have ionic bonds and covalent bonds. Now, you'll learn to split it up differently as you go along, but we'll start off with ionic and compound and covalent, and then we'll split it differently as we move along. But ionic compounds are essentially compounds consistent of non-metal and metal chemically bonded together. Now, a better way of thinking about this is if I have a metal. Now, metals are generally positively charged. Let's just say they're positively charged. So a metal is sodium. Sodium is Na+. Singular charge, that's its ion form. Chlorine, on the other hand, is a non-metal. Chlorine is -1. Because that is a positive charge and that is a negative charge, they like to bond together. They, with their different polarities, bond together. And that is an ionic compound. That is what that is. Covalent compounds, on the other hand, are compounds which consist of only non-metal compounds bonded together. Now, a covalent compound is such as like a hydrocarbon. Now, a hydrocarbon is like petrol. Petrol is a bunch of carbons in a really long chain with hydrogens attached to it. That really long chain, there's no difference in the sort of ions being positive or negative. It's a really important point. So then the ions are not necessarily positive or negative. They're all sort of similar. So essentially, you don't get this difference. You don't get these differences. You essentially just get one long chain. And that is essentially a covalent mixture, a covalent compound. So, electronegativity. Electronegativity will help us bonding a lot more because electronegativity refers to the tendency of atoms to attract a bonding pair of electrons. So, fluorine is the most electronegative element. Electronegativity determines how likely an atom is to attract an electron and form a bond. The difference in electronegativity between two bonding atoms can be used to determine the ionic or covalent nature of the bonds. So as you can see here, fluorine is the strongest. Noble gases don't have any because they don't attract. So all of the electronegativity goes sort of up in this arrow, goes towards this point. So as you move right across your periods, so as I move right across my periods, I become more electronegative. As I move up in my groups, I also become more electronegative. Really important way of thinking about it. So ionic bonds require the transfer of electrons from the metal to the non-metal, whereas covalent bonds only involve the sharing of electrons. So what I want you to think about before is we had these ions. So I had Na+ and I had Cl-. Why was Na+ a thing? Well, if I go back to my periodic table, which was on my last slide, Na is here. So sodium is at 11. So what does that mean for its groups and its shell structure? Bit of a tongue twister, shell structure. What it means for its shell structure is that sodium goes 1s, 2s, 2p6. So it fills its P and its S, and then it starts a 3s1. Who wants to be a 3s1? You're only stable when you have 8 in your outer shell, minus that first shell. So no one wants to have 1 in its outer shell. So what does sodium do? Sodium knocks off one of its electrons and goes, I don't need you. I'd rather be positively charged than have these extra electrons. That's what it does. It knocks off that electron. That electron gets knocked off, and it goes, all right, well, what about a molecule over here that really wants an electron? Well, chlorine really wants an electron because chlorine has 1s2, 2s2, 2p6, so it's got two full shells, And then it's got a 3s2, and then it's got a 3p5. Why would I want to be a 3p5? I'd rather be a 3p6 and be full. That's what it does. It collects another electron. So it collects that electron from that sodium, and essentially by collecting it, they become bonded together. So by knocking off that electron and by chlorine accepting it, they become bonded together. So essentially it has given an electron. Whereas covalent bonding, on the other hand, shares electrons. Covalent actually, they share an electron between the two of them. So the greater the difference in electronegativity forms ionic bonds. So if you have a really big difference, so across this period, sodium has a really, really low electronegativity, chlorine has a really high one, they form an ionic bond. Smaller difference, where if I look at carbon bonding to another carbon, there's no difference there. Therefore, they form a covalent bond because they share that electron. And the different strengths of electronegativity depend on how much they share. So if something's more electronegative, so if I'm looking at two elements bonding together, so I'm looking at carbon and fluorine bonding together, or actually a better example is carbon and oxygen. They bond together a lot. So when carbon and oxygen bond together a lot, think of like carbon dioxide, CO2. They share an electron because they're pretty similar electronegativity, and because there's a really small difference in the electronegativity, as it says here, you form covalent bonds. However, oxygen still is slightly stronger. It's slightly more electronegative. So by being slightly more electronegative, what does it do? It attracts the electron slightly more than what carbon gets. And it's like, you know, probably a terrible example, but it's the only one that comes to my mind. It's like divorced parents sharing kids, and one of them gets them 4 days a week and the other one gets them 3. It's like electronegativity. It's a terrible example, but it's sort of what I'm trying to think of a better example in my mind. I can't think of one. It's like when you're sharing chips with your mate and you eat quicker than them. So it's like, bad luck, buddy. I ate all the chips. Same sort of thing. I'm trying to think of a good example. I cannot think of a good one. So that's sort of what I'm trying to say. But essentially, when these two bond together, this oxygen takes more of the electron. By taking slightly more of the electron, there is a very, very slight negative charge on the oxygen. Very, very slight, just because it takes the electron a little bit more. The carbon, on the other hand, becomes a tiny bit positive. It's very, very slight. We don't even call it positive. We just say it's slightly positive. It's this tiny little bit of positive charge. That difference in sharing the electron makes that molecule polar. So as we talked about earlier, polarity, it makes that molecule polar. Polar molecule. That's essentially what we call that there. So that's what happens with hydrogen and oxygen. Hydrogen and oxygen, it's actually covalent bonding. Hydrogen's actually more like sits over here in terms of strength of electronegativity. So they're actually quite close to each other. Just because of this gap, it's a little bit different. Essentially, these two are actually quite close to each other in electronegativity. And essentially, they have covalent bonds, but the oxygen's slightly stronger in attraction. So, compounds just consist of non-metals, and metal will bond together by ionic bonds. Essentially, as you can see here, you've got a spare one here, doesn't want it, so it gives it over there, and that's an ionic bond. These form between cations, which are positively charged ions, and anions, which are negatively charged ions. Ionic bonds form when electronegativity differences are very different, and you get this table salt example of NaCl. Now, compounds which consist of non-metals chemically bonded together usually do covalent bonds, and usually get molecules that are the exact same. They have no difference in electronegativity, so therefore they're going to share like this. So example, you've got all these here, which are their own, but then they share these two. So this was one from this chlorine, this one was from this chlorine, and now they share them. So covalent bonds form, and electronegativity difference between the non-metals are relatively low. So that's what's going on there. So as you can see, you've got covalent bonds, electrons shared, and then you've got ionic bonds, so electrons transferred. So, bonding. Explore the similarities and differences between the nature of inter and intramolecular bonds. Now, this is more of the important side of things. This is more where I would split my bonding, where I would say, all right, this bonding is intermolecular, this bonding is intramolecular. I like to split my bonding here better than where I did it earlier. So intermolecular versus intramolecular bonds. It's really important you don't get these two words muddled up. You need to make sure you can separate them. Intermolecular, think of it like internet. The internet, you can go anywhere. You can do whatever you want. You can go wherever on the internet you want. Intranet is within a small space. So your school will have an intranet. Maybe you use Moodle, or maybe you use a different program where it's online, you need internet to access it, but essentially it's just shared files between your school. You can only access it through your school. It's got only school stuff on it. That's an intranet. It's an intranet because it's within a system. Internet is over the systems. So think about it in terms of molecules. Intramolecular bonds with an A, they are bonds within the molecule. So they are the covalent bonds where they share electrons. Intermolecular bonds are if I had two separate molecules, so I had a chlorine and a chlorine, and my intramolecular bonds was those covalent bonds between the individual chlorine atoms. But now I've got one of them here, and I've got one of them here. What about between those two molecules? Is there attraction at all? Well, there is, and we call these intermolecular bonds. So they're between molecules. So intra, you give covalent and ionic. Inter, we're going to talk about some different ones, such as dipole, hydrogen, and dispersion. So you need to know this for year 12. They are responsible for differences in melting and boiling point. These are forces that tend to be tested more often. So you have three different forces or three different types of intermolecular bonds. Dispersion forces, dipole, dipole, and hydrogen. Now these go in strength order. Dispersion is really weak. Dispersion is in everything. Everything has a dispersion force. When I pick up this drink bottle, there is a dispersion force between atoms in drink bottle, plastic, and my finger. Yes, it doesn't exactly explain why I'm picking this up. There are other things that explain that, but there is a dispersion force between those atoms. It's literally a thing that happens everywhere. Dipole, dipole are when you have polar molecules. So polar molecules are dipole and hydrogen. Non-polar is dispersion. Polar is also dispersion. There's dispersion between everything. Now, dipole, dipole, you need to be a polar molecule, so you need to have some slightly stronger, some slightly difference in electronegativity, so you need to have a slightly positive and a slightly negative area. And essentially, dipole, dipole is just between any polar molecules. Now, hydrogen are special types of dipole, dipole. So they're a type of dipole, dipole, but they're special. These are between what we call the NOF rule, N-O-F. Hydrogen bonded to intermolecularly, so it's not like a full bond, it's just like an intermolecular bond between a nitrogen, an oxygen, and a fluorine. So if a molecule has a hydrogen and it forms a dipole-dipole bond with another polar molecule that has a nitrogen, an oxygen, or a fluorine, it will form a hydrogen bond. This is slightly stronger than a dipole-dipole and can explain why melting points or boiling points increase a bit more in some molecules that have nitrogen, oxygen, fluorine, or a hydrogen, although they need at least two of them. That's why we call it the NOF rule. Some people call it the FON rule. I call it the NOF rule, the nitrogen, oxygen, fluorine. Now, it also wants you to investigate elements that possess physical properties of allotropy, or allotropy, I like to call it allotropy, and allotropy, probably the better way of saying it. Sometimes I put H in there. And then investigate the different chemical structures of atoms. So, allotropy, I can never say it properly. Allotropy refers to when an element appears in different forms due to the differences in bonding between each form. So graphite and diamond are literally made up of carbon. They are both made up of just carbon. Graphite and diamond look very, very different. So, oh, sorry, this got a bit squished up. I do apologize for that. I should have fixed that. But nonetheless, you'll get the point. Diamond and graphite are both made up of carbon. They're both networks of carbon. So carbon's a really cool molecule. However, diamond is a complex network, whereas graphite is distributed sheets. As you can see back here, this is like a really complex network where everything is sort of spaced out in weird ways. Graphite is just sheets. They're just sheets. Now, diamonds, because of this complex network, are one of the hardest structures we know to man. That's why diamonds were initially so expensive. Not only were they pretty, they were so hard. So hard, we could barely work with them, and we went, you know what? This is cool. Made them expensive, and now they're really expensive. Graphite, on the other hand, is still strong, but it's brittle. So if I smash a piece of graphite, it'll explode. Whereas if I smash a diamond, it's probably not going to do anything. Nothing's going to happen. So as you can see here, graphite has many layers where the carbons connect to 3 others. It consists of easily or even, I think I'm going to say evenly distributed sheets. I don't think it's going to say easily, I think it's going to say evenly. Essentially, the soft sheets move apart as you hit them, and essentially they are brittle, so they break. Now, if you think about it, it's a really good way. Graphite is used in pencils, so you'll find those in pencils, whereas diamonds obviously are in jewelry. Now, ionic networks are referred to as lattices, and that consists of grid-altering positive and negative ions. So these are covalent bonds, remember? So carbon-carbon is covalent. Now, what if I had solid table salt? Table salt is a solid. So that is what we refer to as an ionic lattice, because table salt is made up of sodium and chlorine. It's held together by ionic bonds. What's really important is they have to alternate. They have to have one positive, then one negative, then a negative, then a positive, then a negative, then a positive. Like, they've got to be alternated. Think about it like balls in like a tub, and you've got to have them all alternated perfectly. What that also means is that if I hit that again, if I hit that ionic solid, if I hit a big thing of salt, I will push different layers against each other, and I'll push a positive, like let's just say I had a positive, and then a positive here, and I had negatives here, and I push this layer up, and now there's positives next to each other. They don't like each other. What do? Explode apart. So they are also really brittle. So because of this, we find that ionic substances have really high melting points and boiling points because they're really strong, but they're also really brittle. So if you hit it really hard, it'll just shatter. And that's really not a good thing. They only conduct electricity in a liquid state because they don't have the ability for a charged particle to move throughout when they're in the lattice. If you melt them down and make them into a liquid, well, all the particles are moving, so you can conduct electricity. So this is what I was trying to describe, that sort of image there. Now, covalent networks, as we've already sort of mentioned, we just mentioned the sort of diamond, and we mentioned the graphite. Now, covalent networks are usually they're always made up of nonmetals, but they are usually made with continuous covalent bonding, and they sort of go off into different directions. They usually, again, have high melting and high boiling points, and again, they do not conduct electricity as there's no ions, and the electrons are in a covalent bond, and hence there is no free roaming electrons to conduct electricity. There's no charged particles within covalent networks to be able to move an electron along. So remember, covalents are non-metals. So the only thing that can conduct electricity as a solid is a metal, just a pure metal. A pure metal is the only thing that can conduct electricity as a solid. It's a rule you should know. It's a rule you should stick by. If it's not a pure metal, it's like a singular pure metal, that is a solid, it cannot conduct electricity. Liquids are a bit different because most liquids can, but it varies. Covalent liquids usually cannot. The molecular formula of covalent networks also represents the ratio of atoms, etc. And we'll learn a lot more about covalent networks, particularly in organic chemistry. So covalent molecular compounds are composed of nonmetals that are held together by weak covalent bonding. Physical properties, they're not very hard. They're usually pretty malleable. This is because the covalent bonds have sheets of lattices like grids, which make it easy for these sheets to slide over each other. The only difference is sort of graphite, which is a little bit more break apart, a little bit more brittle, although it does sort of move okay. It's not as brittle as an ionic substance. An ionic substance is super brittle. They do not conduct electricity because they are all neutral. If an aqueous solution is created, they do not dissociate into ions, so again, they cannot conduct electricity ever. So what we're trying to say here is that HCl here is sort of an example here. It can conduct electricity. Sorry, I just got that mixed up. So in an aqueous solution, they do dissociate into ions, so they can conduct electricity. So what I mean by that is, sorry, I got those mixed up again. Essentially what happens is when you put a covalent molecular substance into a liquid form, so you melt it down, you end up with the ions again because there's so much energy there that it breaks those covalent bonds. They're not that strong. So when you break those covalent bonds, your H positive and your Cl minus, if you had HCl, then become ions again, and they're moving through that liquid, and because they're charged, they then conduct electricity. Sorry, I got those completely mixed up. You do conduct electricity as a covalent molecular substance as a liquid. As you can see here are some examples of it, ice, so forth. Now, metallic structures, these are very different because they do move electrons. They do have the ability to move electrons when they are a solid, and therefore the ability to move electrons means they can move a charge. And when they can move in a charge, what does that mean? When they can move a charge, they are able to conduct electricity. So they're really, really interesting in that point. So in that point of view, we really like metals because metals conduct electricity. We put them in wires. We sort of ductile them into wires, and we utilize them in a lot of our our structures and so forth. So essentially what we refer to this as, and this is a really key wording that you need to know throughout this year and you need to know next year, is that metallic structures consist of a sea of delocalized electrons within a lattice of metal cations. This is the metallic bonding model, and it's something that you'll see, and I don't know why there's no images of it here, and I really want to grab up an image. So what I'm going to do very quickly is move across, and hopefully you can still see this. Let me check my recording. You can still see this. All right, we're going to, I don't want my, you can look at my history. Admittedly, it's just slides. Look at it. Lots of slides. Let's just quickly jump in and let's go metallic sea of delocalized electrons. As you can see, I'm a terrible typer. All right, images. Let's find a random image in here. This is sort of what we mean. I think I like these images here, like this. Like what we're trying to describe here is that there's all of the metal exists as like a positive sort of, they exist as like a positive ion sort of in a field. And as much as it's a positive ion, we're in like a field. And because we're in a field, we're a solid, and that field allows the electrons that are available to just float throughout. So they just float throughout. So they're just here and they're floating up here and they come down here and they go down here and they float around. They do what they want. And then a charge gets applied over here and the electrons go, ooh, they take that charge and they go, ooh, and they move throughout and they move it throughout the wire. And that's essentially why we refer to our electrons as having that idea of being like our metals, having that idea of metals as a solid being able to conduct electricity because those electrons are delocalized and there is a sea of them and they can move around. So this is the metallic bonding model. And these electrons are called delocalized as valence electrons break away from the atoms, allowing these electrons to move throughout the lattice. They are held together by a strong electrostatic attraction between the electrons and the ions within the lattice, lattice. So physical properties, they're really malleable, they're really ductile, so they can be pulled apart, they can be smashed, so forth. They can conduct electricity due to already having delocalized electrons, so having that charged particle allows you to conduct electricity, allows the electricity to move throughout, and that's a really important point. They have high boiling points and high melting points, so this is due to the strong electrostatic attraction. So more energy is needed to break these bonds. The metallic bonding model cannot explain the variance between melting and boiling points, the magnetic nature of metals, the various electrical conductivity of metals. So there are some elements of metals which are really different. Some metals are magnetic, some metals are not. Some metals are conductive far more than others. The variance between melting and boiling points is considerable between metals. We don't have a good way of discussing that in terms of this whole metallic bonding ruling. Like, we don't have a good way of doing that, and that's a really important point. There is no good way of discussing that using this whole metallic bonding model that we use. We can discuss that in terms of different models, and it's something that we can talk about. We won't talk about it today. It's something we'll go into detail in class, and it's something that you will be expected to sort of know about. But that's a really good summary for what's going on. And then we're just going to quickly move into naming covalent molecules, and then we're going to do a couple of practice questions just to end off. So naming covalent molecules is really, really important. If you're naming a covalent substance, the one atom that is most metallic, the one that is on the left in the periodic table and usually on the start of the name or start of the molecule, this will be named first, and then you may have to start with a prefix if they're named according to how many atoms they are, and they usually end in "ide." So name the following substances using the table to the right. So you'd have like carbon dioxide, phosphorus trifluoride, so dioxide trifluoride, and then you have D-nitrogen trioxide, so that would be N2O3. So N2O3, and then if you went to the next one, you have carbon monoxide. That's 1, so you'd have 1 carbon, so C, and then 1 oxygen, O. So you can see here, if you're going to name ionic substances, you go a little bit different. So you name with the cation first, and then the anion second. So cations are the atoms with the positive net charge, and the anions are the atoms with the negative net charge. They ended in "ide." So here, and these keep the elemental name. So here you have sodium chloride, potassium chloride. So potassium keeps the element name, chlorine takes the "ide." Lithium fluoride, so LiF. Lithium fluoride. Magnesium oxide. So magnesium oxide is like MgO3 or something, or O2. I don't remember off the top of my head. But again, it's the idea of putting, I think it's O2, MgO2. It's the idea that you're putting magnesium and then you're going oxide. So MgO2. So oxide, oxygen, fluoride, fluorine, chloride, chlorine. So naming ionic substances is a really key skill. You'll get used to it. You'll sort of pick it up as you go as well. Like you'll do more and you'll be like, oh yeah, no, I get what's going on now. Like it's something that you'll get stronger at as you go throughout. So then this gets far more complicated and probably shouldn't all be on one slide, but nonetheless it is. Naming compounds with polyatomic ions. So these form compounds that have both ionic and covalent bonds. So you need to name the cation first and the anion second. There's no prefixes unless the polyatomic ion has one in its name, e.g. dichromate. And when there is more than one polyatomic ion, it is surrounded by brackets. So what I'm trying to say here is that this is probably the best example down here, SO3. SO3 is sort of its own joint thing. I mean, call it sulfite. As you can see here, sulfite. You usually work with sulfate more than sulfite, but nonetheless, sulfite. And sulfite is like, it's a polyatomic ion. It's 2 atoms that form its own ion. It's kind of its own thing. It's a bit of a rarity. It's something you got to get used to. These things are rare differences in what we work with. So as you can see here, the first one here actually really isn't a polyatomic, but nonetheless we'll go through it. First one here, PbI2. So you've got to think about what are our molecules there. So you've got iodine, you've got, let's jump across to our thing, Pb. So Pb is a bit of an interesting one because Pb doesn't have the same name, like the same lettering as its name. So if I find Pb, Pb is lead. Pb doesn't look anything like lead. It's not an L, it's not an Le, it's nothing like that. There are a few of them like that. Another one's like Au, which is gold, and Ag, which is silver. Neither of those look anything like what they're meant to be. Like potassium-wise, potassium K. Like, you know what I mean? There are some that will come up and you just need to be able to know them, or you need to be able to go to your periodic table and find them. So coming back to here. So back to here, we can find that we have our PbI2. So we have lead iodide, or lead diiodide, but we don't call that diiodide. We just call it lead iodide, despite the fact there's 2 of them because it's its own naming. Now, potassium. Now, what do we have? We have sulfite. Now, how do I know I have sulfite? Because it is SO3. Now, yes, I have 2 potassiums, but we don't need to worry about that. We just call it potassium sulfite because it's the cation, like, there's no prefixes because of the way that the molecules are written. You have to write the molecule like this. Because of the sulfite having a -2, you have to have something with a charge of +2 at the front. Now, if it was magnesium, that would be fine, but, or not magnesium, if you had copper probably is a better example. You have copper, that's fine because copper is 2+, but you have potassium, which is 1+. You need 2 potassiums. We don't worry about that. We just still call it potassium sulfite because you can assume from that name you've got 2 potassiums. Now, carbon chloride, again, you don't worry about it too much. You just say, look, it's carbon chloride. Now, lithium carbonate, again, you find carbonate, it's CO3 2 minus. Lithium's going to be 2+. It's going to be 2, so Li2, but you don't worry about it too much because you've got, carbonate is that, so you're going to work with it. Now, there are, as I said, there's no prefixes. However, there are a couple that do. Dichromate is an example of that. Dichromate, why have we got this here twice? I don't know why. Nonetheless, dichromate does come up a bit. Dichromate is a common one that is at the start, so CR at the start, and there's 2 of them, and we still call it dichromate, even though it should just be chromate, but it reads off the tongue well. Not going to complain. One of those ones that comes up a bit. Now, oxyanions are polyatomic anions that contain oxygen, so the suffix ate is used for oxyanions of a given element, so nitrate, sulfate, carbonate, phosphate. For anions with 1 less oxygen, but with the same number of anions, we change it to ite. So as you can see here, we go from nitrate to nitrite, as it has 1 less oxygen than nitrate. For anions with 1 more oxygen, but the same number of anions, we go from ate to per. So instead of saying chlorate, we say perchlorate, as it has 1 more, so it goes ClO4 instead of ClO3. Now, that stuff's very advanced, and it's stuff that you'll learn as you go through. Again, naming acids is another thing that, again, it gets really, really complicated. I think it's probably a little bit beyond where you need to be at this point in time. Naming sort of acids is that next step on in your journey that, again, if you didn't understand it right now, that is okay. I'm just going to leave this slide here. We've got about 10 minutes left, so what I'm going to do is just jump into how to study. I think if you can read through this side and understand, that's great. If you don't worry, you will go through this in class. I think it's a bit too much right now to sort of be adding on to what you've done. So